Hi everyone, today a video on organic analysis and specifically looking into functional group identification. So before we use any proper spectroscopic methods to help us determine what compound we might have made in the lab or what compound we have in an unlabeled bottle, so before we use any IR or NMR spectroscopy, before we use mass spectrometry, these very detailed methods, to tell us what compound we have and what functional groups are present, we can do some simple test tube reactions that are much simpler and often much quicker. We can carry those out to determine what functional groups are present in our molecule. And some of the tests are really easy and straightforward. If the compound shows acidity, well, this might suggest that we have a carboxylic acid. If the compound shows basicity, shows basic properties, and we can test this by kind of reacting them with acids and bases respectively, that might suggest an amine group. If the compound is a solid, well, that suggests that we may have a really long hydrocarbon chain. We have a very high molecular mass molecule, so we have lots and lots of van der Waals forces, or it could be that we have an ionically bonded compound or a very strong bonding between ions. If the compound is a liquid, well, that could suggest that we have a medium length hydrocarbon chain, slightly lower molecular mass, or it could suggest that we have some polarity in our molecule, potentially hydrogen bonding. If the compound is a gas, well, this probably suggests that it's either a very short hydrocarbon chain, a very low molecular mass, or there's very little or no polarity. The only intermolecular forces that we have here are van der Waals forces, the weakest kind. We can also look to see whether the compound dissolves in polar or non-polar solvents. So if the compound dissolves in non-polar liquids such as hexane, then it suggests that we have non-polar functional groups. So overall the molecule is non-polar. If it dissolves in polar solvents such as water, then it suggests we have overall a sort of polar molecule and typically polar functional groups. And a final quick test we can do is to combust the compound, to burn it. And if it burns with a smoky flame, that suggests that we may have an aromatic compound because we have a much higher carbon to hydrogen ratio than we just do in an alkane, for example. So we're going to go through a number of chemical tests that can help us determine what kind of functional group we have in our molecule. And all of these tests are simple test tube tests. We can do them just in a test tube very quickly. And the first is going to be able to tell us the presence of an alkene. And we can test for the presence of an alkene by shaking the compound with bromine water. This is just bromine dissolved up in water, aqueous bromine. Now this is an electrophilic addition reaction. We'll have seen this reaction if you go to look at the alkene series of videos. It's an electrophilic addition reaction that adds the dibromine, the Br2, across the double bond. It forms a dibromoalkane. And the key thing is that bromine water, the aqueous bromine, is orange coloured. If this electrophilic addition reaction occurs where we consume up our bromine, we use up our bromine and turn it into our dibromoalkane, well, that results in a colourless solution. So we have a very distinct colour change of orange to colourless. So the test for an alkene is to shake the compound with bromine water, and if we get what's called a decolorization, i.e. we go from orange to colourless, then we contain somewhere in the molecule will be an alkene functional group, a carbon-carbon double bond. The next one is to test for haloalkanes, and we can test for haloalkanes using something called the silver nitrate test. And this is because different silver halides, so silver chloride, silver bromide, or silver iodide, have different colours for a start, but they also have different solubilities in ammonia. And hence we can first of all tell if we have a haloalkane at all, but also tell the difference between a chloro, a bromo, and an iodoalkane. So the way that we do this is that we first of all take our haloalkane, Rx, and we add sodium hydroxide. Now sometimes you'll see people add sodium hydroxide, sometimes people will add water. Essentially there's no difference between the two. They both act as a nucleophile in a nucleophilic substitution reaction to end up forming the alcohol, ROH. And if we use sodium hydroxide, we form NaX, the sodium salt. If we use water, we end up forming HX. Now the only difference really is that we're using a hydroxide anion versus water as our nucleophile, the hydroxide anions are much better nucleophiles, so the rate of reaction is much, much quicker. So if you do this experiment in school, typically you use sodium hydroxide because the reaction happens very quickly. It would also happen with water, just slower. But if we're using sodium hydroxide, we form our NaX, and then the second step is to take our NaX and react it with the silver nitrate, AgNO3. And what this does, this is simply a kind of simple reaction where the ions just sort of switch over from each other, sort of ion substitution if you like, and so we end up here with AgX, our silver halide, and sodium nitrate being formed. Now an important step in between of those two blue steps there is to acidify with nitric acid, HNO3. And the reason for this is because we may have some impurities in there. We may have some carbonate anions, we may have some hydroxide anions. And when we have the silver nitrate, if we form silver carbonate or silver hydroxide, these are also precipitates and white precipitates. And so this might give us a false positive. If it gives a precipitate, we think, oh, we've got a haloalkane, but actually it hasn't been. It's either a silver carbonate or a silver hydroxide precipitate. And so by adding nitric acid in, we either get the nitric acid reacting with the hydroxide anions to acid plus base gives salt plus water, or we get the nitric acid reacting with the carbonate anions. Acid plus carbonate gives us water, carbon dioxide, and the salt. Now the important thing here is this is normally done after the addition of the sodium hydroxide. So the first step is to add the aqueous sodium hydroxide, form the alcohol and the sodium halide, then to acidify with the nitric acid. And the reason why we do it in between the two steps and not just at the start is because in case we've added any excess sodium hydroxide. If we've added excess sodium hydroxide, in that second step, there'll still be some hydroxide and some sodium hydroxide and hence some hydroxide anions still hanging around that could form a silver hydroxide precipitate. If we're doing the reaction with water, then essentially it doesn't matter so much. We can acidify either right at the start or acidify in between the two steps, like here. So add the sodium hydroxide, add the nitric acid, and then add the silver nitrate. And the key thing is we make our silver halide, AgX. Now, if it's silver chloride, the precipitate is white. If it's silver bromide, the precipitate is cream. And if it's silver iodide, the precipitate is yellow. Now, that already gives us a distinguishing test. We can tell the colours apart. However, the colours aren't the easiest to see. I've put the picture here of on the left, the silver chloride, on the middle, silver bromide, and on the right, silver iodide. And you can see that they're pretty similar colours. And while you might be able to distinguish between silver chloride and silver iodide, the middle one, silver bromide, is very difficult to tell. And actually, even if you just had one of those test tubes, it would be maybe quite difficult to tell whether it's white, cream, yellow, off-white, whatever the colour might be. Colour is very subjective. And so, a better way to do it, a more kind of accurate way, is to use an ammonia solution. And this can be added to test the solubility. And the way this works is that if we add dilute ammonia solution, silver chloride will dissolve in dilute ammonia. And so we have a white precipitate dissolving to give a colourless solution. But the key thing is that silver bromide and silver iodide are insoluble in dilute ammonia. And so those precipitates remain. So if we add dilute ammonia, the precipitate dissolves. It must have been silver chloride, and hence we had a chloroalkane. If we have precipitates that remain, we then add concentrated ammonia. And if the precipitate dissolves in concentrated ammonia, then this must have meant that it's the silver bromide, and we started off with a bromoalkane. We have the kind of cream precipitate dissolving to give a colourless solution. And then finally, if we've added both dilute and concentrated ammonia, and there's still a precipitate that remains, it must be the silver iodide, because that is insoluble in both dilute and concentrated ammonia. Now, the key reason why we add the dilute ammonia first and not just concentrated ammonia straight away is because both the silver chloride and silver bromide will dissolve in concentrated ammonia. So we have to add dilute ammonia first to see if we have silver chloride. If it remains, add concentrated ammonia to see if we have silver bromide. And if that remains, it must be silver iodide. So generally, to test for a haloalkane, add sodium hydroxide, add nitric acid, add silver nitrate. We then get our precipitation of our silver halides. We can tell those apart from the white, cream or yellow colours. Or to be more accurate, add dilute ammonia, add concentrated ammonia, and see when the precipitates dissolve, or if they don't, it's silver iodide. So the next test is to look for the alcohol functional group, an OH functional group. And the presence of alcohols can be confirmed by adding acidified potassium dichromate to the solution. Now this is an oxidizing agent, so it will oxidize primary and secondary alcohols to the corresponding aldehyde or ketone. And I go into a lot more detail on this reactivity in the alcohols series of videos, so go and have a look if you want more detail. But we know that we can oxidize a primary alcohol up to an aldehyde or up to a carboxylic acid, depending on the conditions. And secondary alcohols will be oxidized up to ketones. Now we can't oxidize secondary alcohols any further because we'd have to break a carbon-carbon bond. We've run out of carbon-hydrogen bonds to be able to break, and that requires a much more strong oxidizing agent. And likewise, tertiary alcohols can't be oxidized because we'd have to break carbon-carbon bonds as well, which can't be done using potassium dichromate. Now, as we oxidize up our primary or secondary alcohols, the dichromate is reduced. Remember that if we have oxidation happening, we have to have reduction happening as well. Redox, they have to happen at the same time. And so the alcohols get oxidized, and therefore the dichromate anion is what is reduced. And the important thing here is that this leads to a colour change because we have the reduction of chromium-6 to chromium-3. Chromium-6 is orange coloured, chromium-3 is green coloured. So we have this very clear, very distinct colour change of orange to green. And so if we have a primary or secondary alcohol, we will see this colour change, orange to green, if we added acidified potassium dichromate to the solution of our compound. Of course, this isn't the best test because if it's a tertiary alcohol, this wouldn't give a colour change. We'd still be left with the orange chromium-6. And also, the test also gives this colour change with aldehydes because aldehydes aren't the final oxidation product of a primary alcohol. We can oxidize aldehydes further up to carboxylic acids. Now, this can depend sometimes on the conditions, but if we have excess of our potassium dichromate, once it's oxidized all of the primary alcohol to the aldehyde, we still have oxidizing agent, and then we oxidize the aldehyde up to the carboxylic acid. And this also can happen if we have the presence of water. And so it's not the most definitive test in the world, but it can be used for primary and secondary alcohols. And so the test is to add acidified potassium dichromate, K2CR2O7, acidified with sulfuric acid. And the result, if we have a primary or secondary alcohol, is that we'll go from orange to green. The next functional group is aldehydes. So we've already said that we could confirm an aldehyde by using the acidified potassium dichromate. That's not a very good test though, because it could also show the presence of alcohols. And so a better way to test for the presence of an aldehyde is to warm a solution of the compound with either failing solution, which is a blue solution of copper hydroxide, essentially. And as we oxidize up the aldehyde to our carboxylic acid, we get the reduction of the copper oxide down to, the copper hydroxide down to copper 1 oxide, which is a kind of orange-red colour. And so if there's an aldehyde and we use failing solution, the aldehyde gets oxidized up to the carboxylic acid. The copper hydroxide, copper 2, gets reduced down to copper oxide, copper 1. And so we have a blue to orange change. And so technically we have our blue solution typically going to a red precipitate. Or we can use Tollin's solution or Tollin's reagent. And this forms a silver mirror if an aldehyde is present. So our aldehyde gets oxidized up to a carboxylic acid. And then Tollin's reagent essentially is a complex silver ion. Essentially it's silver 1. And the silver 1, because the aldehyde has been oxidized to the carboxylic acid, the silver must get reduced, so it goes from silver 1 down to elemental silver. That's why we get this silver mirror around. So what we would see is our colourless solution. If there's an aldehyde present, it would turn into this silver mirror lining around the edge of the test tube. And so we either warm with failing solution, which we have a blue solution to a red precipitate if an aldehyde is there, or warm with Tollin's reagent, and we would see a colourless solution change to a silver mirror if the aldehyde is present. And so we can often use this test in conjunction with the acidified potassium dichromate, because we have our acidified potassium dichromate showing us the orange to green colour change for a primary alcohol, for a secondary alcohol, but also if an aldehyde is present. We can also do this test for aldehydes, and if there's no change, then it must have been an alcohol functional group that was present. If there is one of these changes we've just discussed, then it tells us that we actually have an aldehyde group and not an alcohol. The next one is carboxylic acids. And so the presence of a carboxylic acid can be easily determined by adding sodium hydrogen carbonates. This is one of these really easy tests to see whether our compound contains an acidic part. And so we add sodium hydrogen carbonate solution to the compound. And if an acidic group is present, essentially we will have an acid plus carbonate reaction, which is going to give us carbon dioxide, water, and in this case the salt being formed. And the really key thing is that CO2 gas is released. We'll see what we call effervescence, CO2 gas being given off. So to test for carboxylic acids and generally acidity, we add sodium hydrogen carbonate and we will see effervescence, carbon dioxide given off. We can't just add, for example, sodium hydroxide because that's just going to give us an acid plus base reaction, salt plus water. We need to be able to see this effervescence. We need to be able to see the carbon dioxide, so we have to use a carbonate base. So, time to have a go at the questions. If you want to have a go, pause the video and the answers will be on the next slide. But essentially we have a whole series of molecules to distinguish between, and you have to give the distinguishing test and the result of that test. So if you'd like to have a go, pause the video and the answers will be on the next slide. So the answers to the questions of the first one was to describe how we could distinguish between the compounds in the following pairs using one simple test tube reaction to give the reagent and state what you would observe. So the first pair of reagents, R and S. R is a primary alcohol. S is a tertiary alcohol. And remember that primary alcohols can be oxidized with potassium dichromate. Tertiary alcohols can't be. So we would use acidified potassium dichromate, acidified with sulfuric acid. And what we would see is that the primary alcohol would be oxidized up to the aldehyde or potentially the carboxylic acid. The key thing being that it would be oxidized and therefore our dichromate anion would be reduced. We go from chromium 6 to chromium 3 and the colour change that we see is the important bit, orange to green. For a tertiary alcohol, it can't be easily oxidized because you'd have to break carbon-carbon bonds, which we can't do with potassium dichromate, and so therefore we'd see no reaction. And so we'd have essentially just the orange colour of the dichromate remaining. B, we have between T and U. So T is an ester. We have our carbonyl CO double bond, and then we have a single bonded oxygen with an alcohol group of it. That's an ester. U is a carboxylic acid. We have our carbonyl CO double bond and then an OH attached. And so the key difference between these two is that the carboxylic acid shows acidic properties and that we can react this with a carbonate base. And the key thing that we will see, we have an acid plus carbonate reaction, gives us water, carbon dioxide, and salt. The key thing is that we see carbon dioxide, we see CO2 gas given off, this is effervescence. So we could tell which one was the carboxylic acid rather than the ester. And then finally C, between V and W. So C is a diketone. Essentially it doesn't matter that we've got two of them in there, essentially the functional group is ketone. We have our carbonyl group with carbon groups on either side. W is a dialdehyde. Again, it doesn't matter if there's two of them, it's just an aldehyde. We have a carbonyl group attached to a hydrogen on one side and a carbon on the other. And so we can either use Tollens reagent or Fehling's reagent to be able to distinguish between ketones and aldehydes. If we use Tollens reagent, the aldehyde can be oxidized up to the carboxylic acid, while the Tollens reagent, which is silver 1 ions, gets reduced to metallic silver. So we'd see a silver mirror forming. With an aldehyde, ketones can't be further oxidized up because, again, we have to break carbon-carbon bonds, which is not possible with these kind of slightly weaker oxidizing agents. And so we'd see no reaction. It'd still be a colourless solution. If we use Fehling's reagent, then again, the ketone can't be oxidized up easily using this, and so we'd see no reaction. We'd see just the blue solution of the copper hydroxide, which is Fehling's solution. If we have an aldehyde, that can be further oxidized up to our carboxylic acid. And so as we oxidize it out to the carboxylic acid, the copper 2 ions get reduced to copper 1, we form copper 1 oxide. And this colour change is a blue solution to a brick red precipitate. And then question 2 was we have these 4 unlabelled bottles of liquid. We were known that they were either propan-1-ol, propanal, propanoic acid, and 1-chloropropane. So how could we test between all of those? So the propan-1-ol, the way that I if I give this kind of question is to kind of set it out as a table. So I'm listing what the functional group is in each of these molecules. So propan-1-ol is a primary alcohol. Propanal is an aldehyde. Propanoic acid is a carboxylic acid. And 1-chloropropane is a haloalkane. And so now we have to think about, well, what tests can we use to test for these different functional groups. Again, a primary alcohol we can test for by acidified potassium dichromate. We get it oxidized up to an aldehyde or even to a ketone, and the dichromate being reduced, chromium 6 to chromium 3, and we see an orange to green colour change. The propanal is the aldehyde. Again, just as in the last question, we can either use Tollens reagent or Fehling's reagent. If we use Tollens, we would see a silver mirror of elemental silver being formed, our aldehyde oxidized to the carboxylic acid, silver 1 ions reduced to metallic silver. For Fehling's solution, we have our aldehyde being oxidized up to carboxylic acid, and then the copper 2 ions in Fehling's copper hydroxide being reduced to copper 1 oxide, and that's a blue solution to a brick red precipitate. For propanoic acid, it's a carboxylic acid, so we can do the test of acid plus carbonate. In doing this, we're going to see carbon dioxide gas given off, effervescence. And then finally, 1-chloropropane is a haloalkane, so we can do the haloalkane test where we add our nitric acid first, just to remove any impurities that might form the precipitates with the silver nitrate we're going to add. We're going to add our sodium hydroxide. This ends up forming alcohol and our sodium X, essentially our sodium salt, sodium halide. We then add our silver nitrate. This forms our silver halide precipitates. Remember that it's silver chloride is a white precipitate, silver bromide is a cream precipitate, and silver iodide is a yellow precipitate. So we could go off the colours. We'd say that a white precipitate forms with 1-chloropropane. A more precise way to be able to tell is to add dilute ammonia, and this dissolves up silver chloride. And so because we have a chloropropane, what we would see is the white precipitate dissolving with dilute ammonia. So thank you for watching this video. You can find many more like this on my YouTube channel. If you found it helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to email me. I'll be happy to help.